Hello, I'm Norman Wahlberger, and today we're going to look at radian measure as a way of understanding how to navigate around the circle. We're going to inquire as to what it actually is and whether it actually really logically works. We're looking for rational ways of understanding things which are really solid and comprehensible and are based on computational reality. And we are going to have to move away from radian measure. So here we're going to introduce some of the issues. Okay, especially with regard ultimately to uniform motion, which is what we're aiming for, because we understand that to understand a circle, we don't really need a notion of angle at all. We can have a rational parameterization. So it's only when we're going around a circle uniformly that the issue of requiring angles arises. But even after we have decided that we want something like angles, there's still a question of which angular system we're going to use. Okay, so the idea of a radian and a radian measure is relatively recent in the history of trigonometry. It arose first in the 18th century. Roger Coates more or less had an understanding of radians, even though he didn't actually define exactly what a radian was. That was only in the 19th century. James Thomson and then Thomas Muir first illustrated the idea of a radian. Okay, so what is a radian? Well, it's an angle whose arc length on a unit circle is 1. So what we have to do is we have to try to measure along a circle. And let's get something to measure with. Okay, so we're going to try to map out an arc length of 1. So how could we do that? Well, with a ruler we can measure, okay, that's going to be our 1, so it's about 10 or 10 and a half on this centimeter ruler. So what we have to do is we have to measure along the circle about 10 and a half. So, we could kind of do something like this or try to wrap the thing around, and I think we'd get somewhere like over here. Okay? Now, that's not very accurate, of course, with a ruler, and you could imagine some other physical apparatus to do that. We could perhaps take a piece of string, rather, and then try to mold that string around that shape that we've drawn for the circle. It would be easier if we actually had a physical circle made out of, say, wood, and then it would be easier to stretch the string around it. But even so, we recognize that there's an approximate aspect of that, because the physical characteristics of a piece of string are going to be changing when you bend it. Some part of it is going to be contracted, some parts can be extended. It's not entirely clear that the length of the string, whatever that means precisely, is maintained when you bend it. Nevertheless, approximately at least, we can say that, all right, this thing here, that length is approximately 1. And so this is a unit circle, so this angle here in the radian system ends up being a value of 1 radian. Okay, as an expression in terms of degrees, this turns out to be approximately, and I should put approximately here, approximately 56.2957795130823 ... degrees. So converting from radians to degrees or back is something that we can do approximately and invariably invokes these infinite kind of decimals. So it's important to realize that this is not a proper mathematical definition. It's valid at the level of approximations involving approximate uses of rulers or using pieces of string or limiting kinds of arguments. But proper mathematical definition, this doesn't really qualify. Okay, so no, it's not necessary to have a unit circle, and it's advantageous to have a flexible approach about the size of the circle. So we can also define radians in terms of a general circle. So here's a circle of some radius r. And here's a point on the circle, and there's the point on the x-axis, the positive x-axis. And here is a part of the circle from the x-axis to the point in question. And supposing that we have a notion of length of that circular arc, then we can also define the angle as the ratio of L over R. So the ratio of this arc length to the radius length is another way of defining the angle theta as measured in radians. This makes it more clear that the angles in this context are dimensionless because we have dimension of length divided by dimension of length. So technically, that's dimensionless. Unfortunately, this prescription and the previous one presupposes a theory of lengths of curves. So we're assuming here that we have a notion of the length of a curve. And unfortunately, this is a very big assumption, and it's really an unwarranted assumption. So when students are going to university and they're taking calculus, often for the second time, and they're learning about integration, they learn that one of the applications of integration is to define arc lengths of curves. They generally see it only in a rather limiting way, though. So if you have, for example, a function, like y equals f of x, on some interval a to b, the x-axis, defining a curve gamma, then the standard definition for the arc length of that curve is given by this. L of gamma is the integral from a to b of the square root of 1 plus f prime of x all squared dx. So we take this function here, we take its derivative, we square the derivative, we add 1, we take the square root of that, we take the square root, and then we integrate that expression from a to b with respect to x. Okay, so these are all calculus notions. And ostensibly, this defines for us the length of the curve. This is a standard formula, but in fact it's hugely problematic. Okay, it's hugely problematic. And maybe it's a little bit disconcerting to students who have, in fact, been talking about lengths of curve for some time. They've been talking about the lengths of circular arcs for some years, and it's disconcerting to find out that the actual definition of what we mean by the length of a circular arc is in fact reliant on this kind of sophisticated calculus notion. So that throws into question all the previous stuff that they've been doing with angles and circular functions. Because if we're just now defining precisely what an angle is through this calculus formula, then how can we justify having talked about cosines of angles and sines of angles and all those other geometrical things about angles before that? All right, so it's a very logically fraught thing. That's independent of the actual difficulties with the formula itself. Now that formula for arc length, the one that we had star on the previous page, which is really the same as this one here, is very useful in an approximate applied mathematics sense. It is a very powerful formula that actually allows us to obtain specific computational results for explicit curves. But that requires an approximate view of all the ingredients here. Okay? So that involves an approximate view of, first of all, the derivative. Okay, you don't have to take, in fact, you can't really take a rigorous, pure mathematical point of view towards the derivative. You have to take an approximate point of view towards the derivative. In other words, you can't take the limit to infinity. You have to take the limit only to a certain extent and work with finite approximations. When you take this square root, you're not really in a position to take a correct infinite square root because you're doing applied mathematics. You actually want answers, so you have to take an approximate square root. To calculate the integrals are usually defined in terms of infinite processes, but to actually get numbers that you can actually exhibit, you need to truncate those infinite processes and replace them with finite ones. Now, the applied mathematicians are very clever, and they know how to do all of these things. So they know how to avoid all the infinite processes that the pure mathematicians invoke in setting up an expression like this. They can avoid those infinite processes and get explicit, concrete answers, like numbers to 8 decimal places or whatever. And they realize that there's a certain amount of error there, that there's an approximate aspect to what they're calculating. But nevertheless, it's quite useful. So that's in the applied direction. But in the pure direction, as a statement of pure mathematics, this is actually logically rubbish. To be quite honest with you, that's really what it is. It doesn't make sense at 3 different levels. It doesn't make sense because of the derivative. The derivative involves something that you actually cannot do, the current notion of derivative. It also does not work because of the square root. The square root technically involves something, a process, an infinite process, that you cannot actually do. And it does not work at the level of the integral, because that too requires an infinite process that you cannot actually complete. So for the pure mathematician, this is fraught with difficulties. There are infinite processes involved in the derivative, in the square root, and in the integral. These are very serious problems. I mean, the logical structure of this thing is just vacuous. It just does not work. And the theory is really unsupported, except by trivial and cherry-picked examples. When you get around to doing this in a calculus course, you may not know this, okay? The teachers know it, but the students often don't, is that the examples to illustrate arc lengths of curves are either trivial or they're cherry-picked. You have to look at very precise, carefully constructed examples to make this thing something that you can actually calculate and get a real answer for. For a typical function, you cannot calculate this thing exactly. You have to fall back to an applied approximate point of view. But if you want exact answers, only really cherry-picked examples work. Of course, we don't tell our students that. It's kind of a careful secret, but that's the reality of it. Okay, but we have to recognize that there's this distinction here, the distinction between applied mathematics over here and pure mathematics over here. In an applied framework, this is useful and powerful and very reasonable. But from a pure mathematics perspective, it's highly problematic. In fact, the theory really collapses. It really does collapse. It doesn't work. So I want to emphasize this distinction between the pure mathematics and the applied mathematics. There really is a big gap here. And unfortunately, the sociology of things these days is such that pure mathematicians, when they're responding to criticisms like the kind I'm likely to raise, will move over to the applied side and use the techniques and the thinking and the power of applied mathematics to justify what they're doing. So, for example, many viewers may think that, modern mathematics would just collapse if we removed real numbers, for example. Okay, because real numbers are what is being taught at universities, and that ultimately ends up translating to building bridges and rocket ships and transistor circuits and all kinds of things. But the reality is that the building of the bridges and the circuits and the rocket ships and so on is done by applied mathematicians who are really working in a floating point arithmetical system. They don't need an infinite number of decimal places. They typically need 5 decimal places or maybe 10 decimal places in extreme situations, or perhaps if they're nuclear physicists, 20 or 30 decimal places, but that's the limit of it. The pure mathematicians invoking arithmetical operations that are infinite then sort of ally themselves with the applied results, saying, see, the applied mathematicians are doing all these great things with our formulas. But they're not really acknowledging that the applied mathematicians take these abstract formulas with infinite amounts of information and pair all that, truncate it to make it finite and floating point and computational. And that's really where the essence of the computation lies, in the finite computational stuff that the computers are actually doing. Okay? So it's wrong to suppose that the infinite processes of pure mathematics are justified by the fact that we actually get all these valuable applied mathematical outputs. Okay, there's a distinction here, and we need to keep these things separate. So when it comes to the lengths of curves, this is an excellent example of this. Okay, so from an applied maths point of view, you have some curve here. Okay, you want to know what is the length of the curve. Well, the length of a curve, this one here, gamma, is an approximate quantity in applied mathematics, and that works. It makes sense to talk about the approximate length of a curve, or to talk about the length of a curve approximately, where you understand that the length of a curve is something that's going to give you an interval. There's some kind of range of values, and there's an indeterminate aspect about what the length actually is. So, for example, an applied mathematician can always take a curve like this and subdivide it, or sort of sample it at a discrete number of points, closely spaced. And then they can calculate approximate distances between these things. There's a square root involved, yes, but we can do an approximate square root. And so then you can add up these approximate distances and get an approximate formula for the length of a curve. That's perfectly reasonable. So, for example, the length of this curve might be approximately 7.12. Fine. But on the pure mathematics side, the claim that the curve like this has a length, which is a precise, exact, typically real number, is one that is not really valid. The length of a curve is actually not defined as a real, precise value. Some things in mathematics are generally approximate. Other things are precise. What 7 times 8 is, that's a question that has a precise answer. What the length of some general curve is, that's not something that has a precise answer. That's just the way it is. Okay? So we need to rethink a lot of things that we're doing. Okay? We have to acknowledge the difference between precise things and approximate things. And we have to respect the fact that just because we want something to be precise doesn't mean that it is. That's just the way it is. All right, so to carry on with our story about radians and circular functions, here's our unit circle again, and we're thinking now of having a radian measure. So we're going to assume that we have a radian measure temporarily. So what actually happens? So here is a point. There is an angle of theta equals 2. What does that mean? It means that this length here, this circular arc, is supposedly of length 2. It means that if we had a piece of string and we were somehow able to bend that string in the shape of that circular arc, and then we stretched it out, it should be the same as that. That's a physical prescription of what's happening. And then the y-coordinate of that point is what we call sine of 2. Okay, so sine theta then becomes the modern function, which is the usual one that we see, where the independent variable here, say theta, runs from 0 to 2 pi, this infinite decimal that we've seen a couple of times. Okay, that's an infinite amount of decimals going on to infinity. Okay, that's the independent variable, and then we have a function that, of course, looks just like the other one, except that it's been rescaled. And it just corresponds to the y-coordinate, which goes starting at 0 up to 1, and then down to -1, then back to 0, as the point on the circle goes all the way around. So this is the modern definition of the circular function sine theta, where the angle is normalized to be measured in radians. And notably, this is a different sine function from the sine function that has been studied and measured and calculated for most of the history of mathematics. So for 2,000 years, we had a sine function that was measured in degrees. And for the last couple of hundred years, perhaps only about 150 years, we have a sine function which is measured in terms of radians. So in this story, sine of 2, that's 3.14, etc. 2 is maybe somewhere over here. And then the value of the sine of 2 is some number, some real number then, invariably you get real numbers, which is 0.909297426825682 ... Now for an applied mathematician interested in some calculation, some geometrical construction or something like that, then probably only you need 3 or 4 places, and the rest can be discarded. But in terms of pure mathematics, you see what we have here is only a very small part of the story, because there's quadrillions of digits, there's an infinite number of digits in fact to the right here, which we have completely ignored. Okay, so, but this is the typical story, that with this invocation of what a sign is, then necessarily the values of these signs are almost always these real numbers that go off to infinity, and you can't actually calculate them. That's the reality. You can't actually calculate them. So we say things, oh, like it's sine of 2, dispensing the need for actually exhibiting what sine of 2 actually is. So instead of having computation, we end up having symbolical answers to questions. That's modern trigonometry for us. Okay, so now we can ask the question, so why are we actually using a radian system? What's wrong with the Babylonian system that's been around for thousands of years and has been very well studied? So there is an answer, but the answer is largely invisible to high school students and only sort of generally, gradually perceived by undergraduates. And the reason is because there's seeming advantages for calculus and analysis. That's the real reason why we use radian measure. It's not to make trigonometry simpler. It's not to make geometry simpler. It's not to make astronomy simpler. In fact, all of those things become more complicated with radians. It's to make analysis simpler, or at least the current form of analysis. And why is that? Well, it's because in analysis, it turns out that the sine and the cosine functions, which were originally defined in terms of the y and x coordinates of a point going around the circle, those functions turn out to be definable in some other way if we use radian measure. Namely, we have these infinite series to define them. So sine theta can end up being defined as an infinite series. Theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial minus theta to the 7th over 7 factorial, and so on. And cosine theta is 1 minus theta squared over 2 factorial plus theta to the 4th over 4 factorial minus theta to the 6th over 6 factorial plus and so on. These are, again, infinite, and they are interpreted in the modern framework as functions. So you take a real number, an infinite decimal, and you plug that infinite decimal into here. You calculate it, its cubed, its 5th power, its 7th power, and so on. You take this combination with dividing by these factorials. You carry on to infinity, to the end of time. Okay? And at the end of time, lo and behold, you have sine of whatever number you started with. Clearly, this is an arithmetical fairy tale, right? There's no way you can actually do this. But you can talk about it. That's the great thing. You can talk about it. And you can play around with it in certain ways. So you can make algebraic manipulations that don't actually require you to actually compute this thing. Okay, and similarly for cosine theta. Now, so that's nice. So we have definitions of these functions which are now independent of any geometry. Right? There's no geometry here. It's not clear that this has anything to do at all with a circle. It's certainly not clear that these things are periodic functions, which analysts like to think that they are. But they can't actually verify that. I mean, you actually, ask them to make a computation that illustrates the exact periodicity, and they will struggle. There are other advantages, though, once you have these functions set up, because if you invoke the standard story for calculus, then the derivative of this function turns out to be cosine, and the derivative of cosine turns out to be minus sine. And there's a pleasant limiting property that sine theta over theta is 1 as theta goes to 0. And there's a nice connection with the exponential function, which turns out to be seemingly quite beautiful. Many people think that this is the most beautiful formula in mathematics. For what reason, I find it hard to fathom, but anyway, they do. This is Euler's formula. E to the I theta equals cos theta plus I sine theta. And then there's a direct connection with certain integrals. For example, the integral from 0 to x of 1 over 1 minus t squared dt turns out to be the inverse function for the sine function, so the so-called arc sine of x. So there's a lot of calculus kind of advantages. We can define functions by these infinite series, assuming we don't actually have to make calculations about how to evaluate these things. We have formulas for derivatives, we have formulas for limits, we have connections with the exponential, and we have connections with basic integration theory. So there's lots of reasons why analysts are happy to consider these kinds of functions, and then they want to connect it with the geometry, and for that we need to have the angles be radians. Now this is all a classical story taught in pretty well all universities, but we'll see with the algebraic calculus, which is coming soon, that all of this stuff can be rethought. Right? We can think about this in a new way, which is very exciting, but it really does require a major shift in our understanding, and that's going to be a very exciting thing that's going to happen in the next coming years. So you can see that I'm not a big fan of radian measure, and I certainly don't think that it's required for high school geometry or trigonometry. There's no reason that students doing geometry and trigonometry should be studying radian measure. But what if you do want to describe uniform measure? So what system of angles are we going to use? Because uniform motion does require some kind of angular system. Well, the answer, of course, is the one that you probably already feel in your heart. It's the mathematically natural one, which is having a turn, right? Considering going around the circle as being the unit. You go around once, you've gone through a turn of 1. Not 2 pi, not 90, not 100, not anything else. 1. Go around twice, it's a turn angle of 2. Go around this way, it's a turn angle of -1, etc. This is a very natural system, and it suffices to describe uniform motion. So we can then phrase the motion of the planets or physical motion, harmonic motion, in terms of turn angles. But we have to get our heads around what a turn angle is. It's also an approximate thing, but we have to look at it in the right way. So we're going to do that in our next video. Hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.